In this video, I want to take an in-depth look at Cramer's rule as a way to solve linear systems by using determinants. First, I want to show you where the formulas come from, and then I want to discuss how Cramer's rule deals with those linear systems that have no solution or infinite solutions. First, let's consider a linear system with general constant values here. So we have ax plus by equals c and dx plus ey equals f. And both of these are lines because my x and y's have exponents of just 1. And of course, x and y are the variables for which we're trying to solve, while a, b, c, d, e, and f are all just going to be real numbered constants. So sometimes you've seen Cramer's rule given to you this way, that x is the value of this determinant divided by the value of this determinant, and likewise y is the value of this determinant divided by this determinant. But where do all these values come from, and why does it actually work? So first of all, let's go ahead and take all these general values, and I want to find the determinants. And then I'm going to solve this system by using elimination, and I'm going to show you something interesting. Okay, so to find the value of the determinants, we're going to take the major diagonal and multiply those values, and then the minor diagonal and multiply those values, and then subtract. So in the numerator here, I'll have CE minus BF, and in the denominator, I'll have AE minus BD. Okay? So for y, it'll be just the same, AF minus CD over AE minus BD. So something you'll realize quickly is that the denominator here and the denominator here are the same. And that's because those values came from what we call the coefficient matrix. So ABDE, ABDE. So as long as these two are written in standard form, where it's x, y equals your constant, then the coefficient matrix is just going to be a 2 by 2 matrix that's filled with the coefficient values, a, b, d, e, a, b, d, e, and a, b, d, e. So that's why these denominators are the same. Okay? So now that we've seen kind of what this looks like when we find the values of all these determinants, I'm going to go ahead and take my initial linear system, and I'm going to solve it just the way it looks, but I'm going to use elimination. Okay, so no numbers. All we're going to do is look at all these variables and the relationship between them. So let's solve for x first, and we'll solve for x by eliminating the y's. So let's multiply this top equation by e and the bottom equation by negative b. So when I multiply through by the e and multiply through by the negative b, I'm going to go ahead and scale both of these equations. So it looks like I have aex plus bey equals ce. And similarly on the bottom I'll have negative bdx minus bey equals negative bf. So with elimination, we'll go ahead and add these two equations, and of course the y's are eliminated, and that's by design. So we're left with aex minus bdx equals ce minus bf. Well, we're trying to solve for x here, so let's go ahead and factor the x out. So ae minus bd is what's left over on that left side. So let's go ahead and divide both sides by that AE minus BD. When I do that, I see that my value for x is going to be CE minus BF over AE minus BD. Interesting, because isn't that exactly what we saw up here? So CE minus BF, CE minus BF, and then AE minus BD, AE minus BD. So that's exactly the same. So my value of x, looking at it this way after using elimination, could have gone backwards, and we could have actually written determinants out of this. So that's where Cramer's rule gets the value for x. And you'll see the value of y is going to be pretty much the same thing. Let's go ahead and find that as well. So we'll start again with ax plus by equals c, and then dx plus ey equals f. And once again, we'll use elimination. And this time we'll eliminate the x's so we can solve for y. And in order to do that, let's multiply the top equation by negative d and the bottom equation by a. So we'll go ahead and distribute all those values through. And we'll end up with, for that top, negative a dx minus b dy equals negative cd. And the second equation, a dx plus aey equals af. Okay, so when we add these two equations, you'll notice the x's cancel, and again, that's by design. So our y's, let's go ahead and write it aey minus bdy, and then af minus cd. And we'll go ahead and write it that way just so we can keep those negatives in the middle as subtraction signs. And since we're solving for y, let's go ahead and factor that y out. And then we'll divide both sides by the AE minus BD, which we've seen that before, haven't we? So y is all by itself now, and we have AF minus CD over AE minus BD. Okay, so there's my value of y. And let's look back, and we can see that my value of y, AF minus CD, AF minus CD, and then of course we have this denominator AE minus BD, AE minus BD. Okay, so now we know by elimination where all these values come from, but let me go ahead and show you a simpler way to find these determinants. So we're going to go back again and start with our general equation here. Okay, so our x value, we said, was the ratio of two determinants. But where do these determinants come from? Where we said the bottom one was going to be the coefficient matrix. So A, B, D, E. So A, B, D, E. And that's the denominator, no matter if you're solving for x or for y. Well, how about the numerator? Where does this come from? Well, we're going to take our coefficient matrix again, and we're going to put it here with one exception. Since we're solving for x, instead of using the x column, let's go ahead and fill it in with this constant column. Sometimes we call it the constant matrix if you're making it a 2-by-1 matrix. So instead of putting AD, because those are the coefficients of x, let's put CF there instead, and then we'll fill in the BE just the same. Okay, so that is CE minus BF over, of course, AE minus BD, which is the same thing. Okay, so the same thing for y. So we have our coefficient matrix in the denominator, and the numerator is going to be the coefficient matrix again, but because we're solving for y, instead of this y column, we're going to instead use the CF right there, and then just fill in our x's as before. So we have AF minus CD over, once again, AE minus BD. Okay, so we've looked now at solving using elimination on a general system, and we saw where Cramer's rule gets all of its formulas, and then I showed you kind of a quicker way to know what these are instead of having to memorize the formulas. The denominators are just the coefficient matrix, and then the numerators are just the coefficient matrix, but we have replaced one of the columns with our constants, depending on if we're solving for x or solving for y. Next, let's go ahead and take a look at how Cramer's rule deals with systems that have no solution or infinite solutions. So remember, if a system has no solution, it's because the two lines are parallel, which means they have the same slope but different y-intercepts. Okay, so we could say that if we have ax plus by equals c, any system that's going to have parallel lines which are no solution will have the same slope. So it's just going to be a scalar multiple of this equation. So we could say k times ax plus k times by except instead of being the scalar multiple for the constant, because they have different y-intercepts, we will not use. So we'll say D is not equal to Kc. Okay, so we'll kind of just put that aside. So here's our system, and this ultimately will have no solution because this second one is a scalar multiple of the first one with the exception of the constant, which is different. So we're saying these lines are parallel, so they'll never cross. Okay, so let's go ahead and now use Cramer's rule. So the denominator will be the coefficient matrix, so A, B with Ka and Kb. Okay, well how about my numerator? It's going to be the coefficient matrix, but my x is going to be replaced with Cd. Okay, and then here's B and Kb. So let's go ahead and find that value. So we have Kcb minus dB over AKB minus AKB. Oh, interesting. So this ends up being CKB minus dB over 0. And what did we say before? D is not equal to Kc. So if D is not equal to Kc, then the top will not be 0. So Cramer's rule will deal with this by saying when you put all these values in, the denominator is 0, but the numerator is not 0. And that will be no solution. Let's look at the y just for good measure. Okay, so in the numerator, we'll have the coefficient matrix, but instead of this second column with y's, we'll use the c and the d. So here's the a and the ka, and here's the a, b, ka, kb. So in the numerator, we have ad minus ckA, and in the denominator, abk minus abk, which again is 0. And because d is not ck, then we know this is, so ad minus ckA, which is not 0. So again, here's what a system looks like when there's no solution, and this is how Cramer's rule deals with it. The denominator will always be 0, and that's because from our coefficient matrix, one equation is just a scalar multiple of the other, but the numerators will not be 0. So division by 0, that'll give you no solution. Finally, let's go ahead and look at how Cramer's rule deals with a system that has infinite solutions. So remember, in order to have infinite solutions, the lines are coincident, which means one lies on top of the other. And as far as the equations are concerned, one equation is strictly a scalar multiple of the other. So if we have ax plus by equals c, we're just going to multiply every single term by k. So kax plus kby equals kc. So as soon as we go through here and start to solve this using Cramer's rule, we'll notice a lot of things happen right away. So here's our coefficient matrix in the denominator. And for x, we'll replace the x with c and kc. And here's our b and kb. Okay, so here we go. So ckb minus ckb over akb minus akb. So we actually have 0 over 0. So you'll notice it's the division by 0 again, but the numerator is also 0. So this means we're going to have infinite solutions for this system. And that's because everything in the numerator cancels out to 0 and everything in the denominator cancels out to 0 because one equation is strictly a scalar multiple of the other. And you'll see that y will do the same thing. We'll go ahead and do it just for good measure. So here's my coefficient matrix in the denominator, and we'll replace the y column with ckc. So here's aka. So akc minus akc all over akb minus akb. 0 over 0 again, you'll notice again division by 0, but our numerator is 0 as well. So in general, Cramer's rule will always work, and it works for any linear system, no matter the relationship. If the values come out to be, numbers, so x is a number and y is a number because the two equations intersect at a single point, then this will work very nicely, and we'll get a ratio, and we'll just simplify the fraction, and whatever x is what it is. Whatever y is what it is. But in those circumstances where possibly there's infinite solutions, or as we saw before, no solution, then we'll have this interesting situation where you're either dividing by 0 and the numerator is not 0, and that's no solution, or you're dividing by 0 and the numerator is also 0, and that's infinite solutions. So there's an in-depth look at using Cramer's rule on any 2x2 system of linear equations, and it's good for everything. And hopefully that was helpful to kind of guide and steer you in the right direction. So be sure to subscribe to my channel for more upcoming math videos.